Okay, well, welcome back. Our time here is winding down, right? There's just 3 lectures left. And today is will be sort of an action-packed lecture where I'm going to start, I have the outline here. So I'm going to start with a recap of stable reduction and sort of the general strategy of stable reduction and what we used to prove stable reduction in characteristic 0. And then I would like to give sort of an explicit example of how this works in practice, computing the stable limit of a degeneration to a ramified cusp. And then we'll wrap up this discussion of stable reduction, where we'll prove that the stable limit is unique, which will ensure that that the stack is separated. And yeah. And then the last thing we'll do today is discuss some sort of canonical maps between these moduli spaces of pointed curves, of how you can glue marked points together. This will allow us to define boundary divisors on the moduli space, and then also the forgetful morphism. And we'll show that if you forget a marked point and then stabilize, that is contract the rational bridges, we'll show that this is a universal family. So that's the plan for today. So let's get started. Okay, so here's our quick recap of stable reduction. So the statement, you can read it in the theorem, but let me sort of just spell out what it is in this picture here. So I'm only going to spell out the unpointed case, that is when there's no sections, when n is 0. And so we're given a stable curve C star over the generic point of a DVR. And given that, the statement is that then there exists after possibly an extension of DVRs, that is a map like this, that takes t to the n. And then after possibly this extension and then taking corresponding base changes, then the goal is to show that there exists a family C over the DVR that's a stable family, restricting to the original one. And this is just the existence part of the stable reduction. Right, and we care because this implies the existence part of the value criterion for properness, and this is our strategy to show that NGN bar is proper. And when combined with the separated statement that we get at the end, the uniqueness of the limit, we will establish, at least in characteristic 0, the properness. All right, and then the strategy was the following 5 steps. You first reduce to the case where the generic fiber is smooth by considering the nodes and taking partial normalizations, and then using sort of the fact that the stability of curves behaves well with respect to normalization. And then by using the properness of the Hilbert scheme, essentially, you can find some flat limit. And then so C is now a surface. It might be a singular surface, and you might have no control over the central fiber. So then you use sort of embedded resolutions to find a smooth surface, C tilde, dominating C, and such that the central fiber is then set theoretic normal crossing. So you get sort of, by using embedded resolutions, which is an important result. You get almost what we want, but you get that at least the reduction of the central fiber is reduced. Is it in the nodal curve? And then to get rid of the multiplicities on the exceptional components, we argued that you could just take a ramified base extension and then normalize the base change. And then you can arrange that the central fiber is reduced in nodal. And then you're sort of in the situation of a family of nodal curves, like a semi-stable family or a pre-stable family of curves, and then you can contract the rational tails and bridges. That is, you take the corresponding stable model. And we showed more or less that this works in characteristic 0. And right, but somehow the method to prove it doesn't always. Sometimes there's some additional steps and techniques that you need to actually compute what the stable limit is. And that's often in practice sort of important, where maybe you're given a family, a specific degeneration, and you want to know what explicitly the stable reduction is. And so I like to take some time and give an example of how one can work that out. So sort of the biggest challenge in computing the stable limit is in this step where you're step 4, which was computing the normalization after a base change. And so in practice, it's sort of nice to factor this base change into a composition of prime order base changes, because then you can have more control over what the normalization of the base change is. And so we're relying, I should also say I'm sort of following very closely here the exposition in Harrison-Morrison, which is sort of my go-to resource for examples and discussion on stable reduction. And so the proposition we're going to use is written here. And so we're assuming we have a generically smooth family of curves, and such that the reduced central fiber is nodal. And then we define the divisor. As a divisor, the central fiber breaks into irreducible components, and we record their multiplicities. And the claim is that when you take a base change by t goes to t to the p, where p is prime, and you take the normalization c tilde prime, then the claim that this is a branch cover and it's ramified over the reductions of the multiplicities mod p. And so this is what we'll use. Yeah, and so the example we're going to look at, I mean, there's many examples you could take. They're all sort of slightly different techniques are involved. So we'll take a generically smooth family of curves over a DVR degenerating to a ramified cusp. So here the central fiber becomes is a singular point. Right here, maybe I should just here. T will always be a coordinate in the DVR that's a uniformizer. So when T is 0, the central fiber C0 is not stable, right? And P is a singular point. It's called a ramified cusp, like a higher cusp. Right, when t is 0, the equation is y squared is equal x to the 5th. And the question we'd like to know is, what is the stable limit? So in this case, we've already found some limit, and it's a particular singularity, and we want to follow this procedure to decide what exactly what stable curve is the limit. So we're going to follow the procedure we had, but I think to start with, since we already have some limit, so we sort of start with that what I numbered the third step. So we start with blowing up points in the central fiber in order to resolve the singularities. Right, again, and I've sort of cheated. These calculations can be quite involved. As you know, like I think it's these kind of computations are often best done on your own. And they're often very difficult to do at the blackboard. So I've sort of cheated by already writing down the pictures nicely on the left-hand side, and I'll try to show you how the computations work on the right-hand side. So we're starting right now. We're working with this surface here, right? And now we are in the first blow up. We're going to blow up that point P. And so I'm going to work out the computations on the right-hand side. And so let me just introduce the notation I'm using. So like C is always going to be the surface I'm blowing up, and I'll replace that with C tilde, blowing up at a point. And then the preimage of P is this exceptional divisor E. And so we can compute the blow up in 2 charts. So in chart 1, I have one open U1 in the blow up, and X tilde, Y tilde are going to be always my local coordinates in either chart. And in the first chart, they get mapped to X tilde, comma, X tilde, Y tilde. And the second chart does something similar. And note that the exceptional divisors in the first chart is defined by X tilde and in the second chart by y tilde. All right, so let's try to compute the first blowup, and let's look at what happens in the first chart when I take the pre-image. Right, the original central fiber is y squared equals x to the fifth, so y squared minus x to the fifth, and if I compute the pre-image in the first chart, y becomes x tilde y tilde squared minus x tilde to the fifth, which factors as x tilde squared y tilde squared minus x tilde cubed. And x tilde in this chart is the equation of the exceptional divisor. So I get two copies of E1. And so E1 is what's written is this rational curve here. And I'm keeping track of the multiplicity in green. So 2 is the multiplicity. And this here is the blue curve. So it's sort of like a partial normalization of the ramified cusp. This is cuspidal. Great, and now moving forward, let's compute. So now we're in this situation, and now we want to blow up the singular point again. So now we blow up the point P again, and I'm going to now compute this blow up in two different charts. So in the first chart, now my original equation going just for the x tilde is to the x's is x squared y squared minus x cubed. So this is the equation of the central fiber in this. So I'm sort of changing my variable again. So now local coordinates on this are x and y, and local coordinates on the blow up will be x tilde y tilde. And then in the first chart, if I work this out, this becomes x tilde squared times x tilde y tilde squared minus x tilde cubed. And if I factor this, I get x tilde to the fourth times y tilde squared minus x tilde. Right, and so the x tilde, is the equation of the new exceptional divisor E2. And this is, the blue curve. Let's call that D. Okay, so this is computing in the first chart. And when I do these calculations, I always do each chart every time, just so that I don't have to think about where the action is. Here I'm cheating a little bit because I've done this calculation and I'm already showing you, which chart is the relevant one. But let's just see what happens in the second chart, because we should be able to examine the intersection of these two components. And so we do the same equation, and x squared y cubed becomes, maybe I'll spare you the calculation here. It just becomes x tilde squared y tilde to the fourth times 1 minus x tilde cubed y tilde. And here the exceptional divisor is this y tilde, so that's E2. This is the first exceptional divisor, and then this is the curve D, and then in this chart it's smooth. Right, and you see as we're going along, the singularities are getting better, but at this point there's still an intersection of this sort of like parabola tangentially to this second exceptional divisor. So we blow up again, and here we're going to just look in the second chart, and so we're looking at this equation, x to the fourth y squared minus x, and we're computing its pre-image in the second chart. And this is x tilde to the fourth y tilde to the fifth times y tilde minus x. And so here, okay, now in the second chart, this is the exceptional divisor, which I've called F. This is the second exceptional divisor, E2. And now this again is my curve C. Right here, or no, I'm calling it D, sorry, D. This is sort of the partial normalization sorry, not partial normalization, the normalization of the original central fiber. Right, but now we still have sort of this threefold singularity here, multiplicity three singularity. Right, it's three lines meeting at a point, and so now if we blow up one more time, we can separate them. So finally, in the fourth blow up, let's look at the pre-image of this equation, x to the fourth, y to the fifth, y minus x, and it becomes, well, maybe I'll spare you the calculations, just x tilde to the 10th, y tilde to the fifth, and then y tilde minus 1. And now this is the equation of the new exceptional divisor, which I call G, has multiplicity 10. That's sort of the important point. We're doing these calculations to record the multiplicities. And then this is F, and then this is the curve D. And so we've resolved, we're in the situation where we've, explicitly computed an embedded resolution. And now we need to deal with the issue of the multiplicities.
Can you explain here how you ignored the t coordinate in these blowups? Like you work in special fiber somehow.
Yeah, well, I guess I'm just computing the pre-image of the central fiber where t is 0.
Right,
I don't know if that really...
If you compute the blowup, it should include the other fibers too somehow, right? Usually you have to blow up the whole surface, but somehow you've set t to 0 in these computations.
Yeah, I guess that's right. I've only the coordinates I'm working with work globally, but I've set t when t is 0, you get the equation of just the central fiber. I'm just computing that pre-image. Yeah, I guess I don't have a good answer for you. I think you sorry. Right, so the upshot is now we're in a situation where, okay, I spelled out, here's where we are. We have this family, and we have multiplicity. So I write the central fiber C tilde 0, with multiplicity as D plus 10G plus 5F plus 4E2 plus 2E1. And I now have some choices of which base changes to apply. I could either base change by t goes to t to the fifth, or I could go t to the t squared. I think doing it this way first is easier. So I base change by the prime 5, and I normalize. And so what that tells me, if I look at this, the only coefficients that are not divisible by 5 are d, e2, and e1. So that tells me that the normalization, this proposition on the right-hand side, is going to tell me that the normalization is ramified over D, E2, and E1. And so we just need to compute what's the pre-image of the other curves. So namely, let's compute the pre-image. Let's call this map pi, and let's take pi inverse of G. Let's call that G prime. And this maps to G, right? G was the exceptional divisor. It's just a P1. This is a 5-to-1 cover. And we see that it's branched over, well, where does it intersect the ramification locus? It's at 2 points. So it's branched over 2 points, each with ramification index maximal, so 4, 5 minus 1. And this allows us to compute via Riemann-Hurwitz what G prime is. Tells us that 2 times the genus of G prime minus 2 equals the degree 5 times 2 minus the genus of P1 minus 2. So that's a minus 2 plus the ramification. But the ramification is 2 times 4. And so this tells us that the genus of G prime is 0. So G prime is also rational. And on the other hand, let's take the preimage of F, so F prime, let's take that to be the preimage of F. This is a 5-to-1 cover of F, but it's unramified, right? If you look at this picture, F doesn't intersect the ramification locus, and P1 doesn't have any non-trivial unramified covers, right? So this tells us that the preimage F prime is the disjoint union of just 5 copies of P1.
Jarod,
And could you say
again how you know the ramification index in the G prime to G at those 2 points?
That's a very good question, Hannah, and I don't want to try to answer. Let's okay. Hold off that for a discussion. That is good. Yeah, that's a good question. I had the same issue. Yeah, I had the same. Yeah, I struggled with that same issue when I was preparing it, but I don't want to touch that detail now.
Okay, thanks.
Sorry, but so on the right you wrote that it is branched over something that include coefficients, right? And you are not.
Yeah. It's what the right-hand side tells me is that it's ramified over all of the components whose multiplicity is not divisible by 5. Sorry,
so that's yeah, and so that's not also the coefficients. So that does not give you also the coefficients. So
right.
That what you wrote is not exactly the coefficients you want.
Oh, sure. I just did it like set theoretically. Yeah, I'm not including the index there. Correct.
So I is a 0 when P divide the hit, and otherwise it is 1. So that coefficients, you know.
What do you want me to? You want me to write union instead of plus there? Like it's ramified over the union of D, E2, and E1. Yeah, I agree with what you're saying. Yes, it's not 4. Yeah, I understand what you're saying, but I can't really have it. Yeah, I don't really have anything more to say there.
Okay, sorry.
Let me go on. There's a good lot. These are all good questions, and but let's postpone them for like the discussion at the end. Okay, so but the point the reason we did this is because we're trying to decrease the multiplicities. So what happens now is if you compute what the new central divisor, what the new central fiber is over, let's do it over the original DVR, the new central fiber is C prime 0. And so what happens to, it was ramified over D, so we pick up now 5 copies of D, and there's 10 copies of G prime plus 5 times, and then I have 4 E2, but that becomes a 20 E2 plus a 10 E1. But this was over delta. If we compute this over delta prime, I just divide everything by 5. I get D plus 2 G prime plus the sum of these plus 4 E2 plus 2 E1. So the upshot is that we've decreased some of the multiplicities. And so now we're in sort of this picture here, where we have a family where the reduced central fiber is still nodal, and it sort of looks like this, where the only multiplicities we have are at G prime, E1, and E2. And so now we compute the base change, t goes to t to the squared, and normalize, and we know what we're going to get is going to be ramified over D plus F1 all the way to F5. And so we do the same sort of Riemann-Hurwitz calculation to determine the preimages. So we have let's call this map pi again. We have, we're trying to compute, let's see what happens over G prime. So the pre-image, let's call it H. I've defined as pi inverse of G prime. This maps 2-to-1 cover to G prime, which we know is P1. And we know that this map is ramified if you over 1, 2, 3, 4, 5, 6 points. So this is the important point. So now Riemann-Hurwitz tells you that the genus of H is 2. Right? If I take a 2-to-1 cover of P1 ramified over 6 points, I get a genus 2 curve, and it's hyperelliptic. And you also know that H intersect D. Let's call this now point Q. That's this intersection point. This is a ramification point of the 2-to-1 cover. So some people call this a Weierstrass point. And so this decreases the multiplicities of everything except for E2 down, and which is now 2. And so we're getting closer to computing the stable limit. We do this process one more time, which is this step is kind of, it doesn't really change anything other than decreasing the multiplicity of E2 to 1. So now there's no multiplicities. And we have a central fiber that's reduced and nodal. And so we proceed with the last step, which is to contract all the rational tails. And we see what that does is just removes all of these Fs. All of them, these guys get contracted, and you're left with this central fiber here, right? And this is the stable limit. This was my goal to show you that the stable limit of this ramified cusp is the nodal union of a genus 2 curve with the normalization of the original central fiber joined at a Weierstrass point of the genus 2 curve. But this procedure, I mean, I think this discussion raises more questions than it answers. First is that, like, you can ask what exactly, which genus 2 curve is it? Or maybe more generally, what happens if you consider different degenerations? Like if you consider, in fact, you can consider kind of universally in the deformation space of this TAC node, you can consider degenerations like this. And you could ask, yeah, how does the limit depend on these functions AI? And I think, yeah, I won't say any more than that, but if you want to read about it, I would recommend looking at Harrison-Morrison. Right, yeah, I think, it's a good time to pause for questions. And I know there's a lot of details there, and I don't I probably won't be able to jump into any further details than I've already provided.
Can this method be made completely algorithmic?
That's a good question. That's a fair question. Like, I don't know, probably, but like in practice, like it seems sort of like it's like similar to like these qualifying exam problems of computing the number of finite groups of a different order. I feel like each different stable reduction you do sometimes requires different methods and some cleverness of how exactly you apply Riemann-Hurwitz to figure out what it is. And also it depends on how explicit do you want the answer? Like what do you want the output of your algorithm to be? Like here, I was sort of just happy of knowing generally what the topological structure of the central fiber is and not like pinpointing precisely which curve and the equations defining it. But yeah, it's a good question.
I think that Timothy Dockschitzer has made a very similar algorithm or I should say, made something algorithmic which is very similar in figuring out the stable reduction models of hyperelliptic curves, let's say, over a residue characteristic to a local field.
Mm-hmm. Who was that? Just so I can write down the reference.
Timothy Dockschitzer.
Okay, I don't know how to spell that last one. Dr.
DOKCHIT. Dockschitzer.
Like that.
Yeah. ITSER, I think.
Okay, I'll leave it like that.
Sorry. If the chat were on, I could put it in the chat, but
oh great, yeah, put it in the chat.
Yeah, I mean, I think he actually wrote software somewhere that computes these models of stable reduction, but not I don't recall if he has an algorithm for let's say where this is in terms of t or over a field that has a variable t, but I'm pretty sure he did this when the field is mixed characteristic 0, 2, for instance, which is harder than mixed characteristic 0 on an odd prime.
Mm-hmm. Yeah, great. Actually, let me get the name right. Can you just spell it correctly? Just
DOKCHI that's a CHI TSER.
Oh, ER. Okay, wasn't that bad. Okay, Timothy Dockschitzer. That's great. I'd be interested to check that out. Okay, that's. Oh yeah, maybe like moving on. Let me wrap up the stable reduction argument by showing you the uniqueness of the stable limit. All right, so this is the separatedness statement. And well, you can read what's written here, but let me just explain, in a picture here. We're gonna assume that there's no mark points, and we're gonna assume that the generic fiber is smooth. And so we're in the situation where we're given stable families C and D over DVR that restrict to isomorphic curves over the generic fiber, right? We have an isomorphism alpha star of the generic fibers, and our goal is to try to extend that isomorphism. And so what we know is that the total family C, we know that the local structure of both of these stable families, that if I have a point that is a node in the central fiber, then the local structure of the surface is xy equals t to the n plus 1. Like when n is 0, yeah, then it's a smooth point of the surface, but when n is positive, when n is larger, you get an an singularity. And so the first thing we're going to do is just resolve these singularities. So we take the minimal resolutions. So we take C min mapping to C and D min mapping to D. So now that these are smooth, and in order to compare them, we want to sort of dominate them by another smooth surface. And so that the strategy here is you could take the graph of or that is, you take the image, the closure of the image of the graph, and then take a minimal resolution of that. And so that gives us gamma min mapping to both of these, where everything here is smooth. It's also smooth, smooth, smooth. And then you can realize, so in step 3, both of these maps are birational maps of smooth projective surfaces. So we can use the invariance of the pluricanonical sections of under these birational maps. And that tells us that there's an equality of pluricanonical sections here. And the point here, the reason this works is because they're smooth and projective, then they're sort of isomorphic in codimension 2, the relative dualizing sheaf is a line bundle, and so you can compare sections on a large open and not. It's sort of a similar argument to what you'll find in Hartshorne when he shows the invariance of the geometric genus that it's a birational invariant. And then proceeding this way, right? Since we know this, these are all equal, but these are all these essentially define the relative stable model. So moving to step 4, C and D are in fact the relative stable models of these of C min and D min, which are isomorphic. Namely, we know that C is the proj of the relative dualizing sheaf of the sections of this. And we also know the same is true for D. And so because of these equalities of sections, we get equalities of their projes, and so therefore we get an isomorphism between C and D. Right, so that gives us, that's the desired conclusion that we've extended the isomorphism. Let me just explain, because it says this is sort of also the argument that works in for separatedness in higher dimensions for moduli varieties in higher dimensions. But in the case of surfaces, one can make this argument even more explicit. I'm not going to go through the full details here, but let me just sort of recap this argument. We sort of start. We start by taking these minimal resolutions, and let me just erase this. And then we dominate it by a minimal resolution of the graph. So we are sort of in this picture, and one can show directly that gamma min maps isomorphically to C min and to D min. And namely, so the strategy is that, if they're not, these are smooth birational maps. Sorry, these are birational maps of smooth projective surfaces, and we have a structure theorem that we know that there are compositions of blowups, and so that if they're not isomorphic, there must be an exceptional P1 in gamma min that is contracted under one but not the other. In other words, there's some E inside here that under this map gets mapped to a point, but under this one gets mapped to something else, ED, let's call it. And on the other hand, let's also look at the pre-image of this ED. This map is pi, let's call it pi inverse ED, maps to this, and it contains E, but it might also contain more, some other exceptional divisor F. And so we just realized, we sort of play this game where we look at the self-intersection of ED. And that is, we try to get a conclusion, a contradiction by looking at the self-intersection. And on one hand, we know how blowing up affects the self-intersection, that we know that the self-intersection of ED squared is at least greater than or equal to -1. But on the other hand, since it's an exceptional curve by the Hodge index theorem, it's negative. So this already tells you that it better be -1. So it's a -1 curve, but we know that this is a minimal resolution, and that this map does not contract any smooth rational -1 curves. And what that tells you is that this exceptional component is not isomorphic to P1. That is, this exceptional component is singular. This resolution resolves that singularity, so there must have been some intersection here. And so you actually get a contradiction by looking at the self-intersection. Anyway, that was very quick. Maybe I should have not even tried to give that. I'm sorry. But the important point is what this argument gives us. It gives us separatedness. So now we have both the existence of a limit and the uniqueness of the limit, and we get that mg bar is proper. We've shown this in characteristic 0, but it is true that it's proper over spec Z. And the separated statement alone is what we use to get the coarse moduli space, right? As input to the Kiyomori theorem was the separatedness hypothesis. So we apply that, we get a coarse moduli space, and this is a proper algebraic space. So that was sort of the goal. yeah, any questions before? This is sort of like, yeah, half a breaking point of the lecture. Any questions? Yeah, the next topic is going to be on these sort of contraction, or these gluing and forgetful maps between moduli spaces. Yeah, I went through this argument pretty quickly, but part of my point is that there's like, there are sometimes many ways to make these arguments. I wanted to give multiple perspectives. Anyway, so yeah, the next topic is gluing morphisms. And the reference is Knutson's articles, namely his second projectivity paper. And so our goal is to define two types of morphisms. The first takes a genus G curve and a genus G prime curve and glues, say, the two end mark points, right? So we glue the nth mark point to the n prime marked point. And this map should just glue these two sections, the green curve to the purple one. And the other map sort of takes a genus G curve with n marked points and just glues the last 2 points together. And what we want to show is that this is a well-defined process. I mean, even over a fixed field, yeah, I mean, it's sort of conceptually clear how you glue points together, but we also need to work through the algebra, and we need to show that this works in families. So like we need to show this construction works in families. And this does take some work. And I like some of the other topics we've covered last time, I'm not going to be able to cover the full details of this. I'd rather show two different approaches to establish this. And so I'm going to give a sketch first of this first map. So let's call this first map, let's break it into two parts. This is A and B. And so let's assume that we're in just to simplify the notation, the general case is no harder. Let's assume n equals n prime equals 1. So we're given sort of two families of stable curves, C and C prime of different genus, and they each have one section, sigma and sigma prime. And what we do is we just glue them by taking the push out. And so the push out here exists by result of Ferrand. So yeah, I think, yeah, you should, on one hand, push outs can be very tricky in algebraic geometry, and often I think people are very hesitant to use them. But on the other hand, in restrictive settings where one of this is, where, at least in this case, these are both closed immersions. And in this setting, like the existence of push-outs as well as the property of the push-outs are not so bad. So we're going to use the existence of push-outs here, and that they're sort of well-behaved. More generally, they're well-behaved when, so maybe I'll write over here, this well-behaved, they exist and their properties are well-behaved when one map is a closed immersion and the other is finite. But in this case, they're both closed immersions, and so we can take the push out, and what we need to show is that the push out is the desired family of stable curves, and what we're going to use is that the push out is an État local construction, and we'll use the local structure of smooth maps. We note here both C and C prime are smooth along these sections. So what that tells you is it reduces the push out computation by taking, yeah, like the using the local structure of smooth maps, where we can just consider this case where you're gluing in the 0 section. So here A would be your base S, and we need to compute this push out, where both of these are. So this is sigma, this is sigma prime equals 0. And in the affine case, the push out is just the fiber product of the rings. And this is what you can just compute directly. All right, what is this? These are just sequences of two functions, f and g. Let's say f is in the variable x, g is in the variable y, such that they have the same constant. And so you see directly that this is a adjoin x comma y mod xy, right? Because this is the ring of polynomials where you have a constant plus something with positive terms in x and then plus positive terms in y, but there's no mixed terms x, y. And we just, yeah, and we see what we get is a nodal family. So this implies that C tilde over S is a nodal family. And then there's some details you need to show that it's flat and proper. And then you show that it's like the stability can be checked on fibers. Okay, so there's a number of details here to check, but this is one strategy. The second strategy is actually pretty is similar, but we're going to use a proj construction.
Jarod, I'm sorry to pull you back earlier, but in B, like in A, I see what's going on. You have 3 points, then 3 points, you get 5 points. But what happened to the bottom left point in B?
Bottom left point. Oh, sure. I could, yeah, no, that should be there too.
Oh, okay, all right, thanks.
Yeah, I didn't mean, yeah.
Okay,
yeah,
no,
that should be there.
all right, thanks.
Should the genus increase as well for the map in B? G
Oh,
plus
yes.
Yeah.
Oh, yes. Yes. Yeah, good point. Thank you. Yeah, right. Mm-hmm. Okay, so I want to quickly explain how you could also do this with the proj construction. And in fact, both of these methods can be, I mean, they're quite similar. I mean, we know, what we know here is that if I take the relative dualizing sheaf, sigma, or sigma prime over S, that these are both ample. And we're going to use the exact sequence that you have omega C sitting inside the twist to the structure sheaf of the section. And so what this gives you is when you take twists of this tensor K, this maps to O sigma, for all K, and that I could then take the fiber product. So I could, okay, I have this. First thing I could do is push this forward under pi. And I could also do the same with pi prime. And then I take the fiber product of these sheaves, and I call that AK. And then I check that C tilde, which is the proj of this over S, is the desired stable family. So in other words, I'm taking, this is sort of similar to the pushout argument because I'm defining the graded ring, this graded ring as a fiber products of graded rings, like via this diagram. So there's more details to check here, yeah, but this gives you an alternative method. Any questions on these two approaches? And let me quickly, okay, I won't go through the details as much, but let me explain how you can glue these in the second example. Here we're given a family of stable curves and two sections, sigma 1 and sigma 2. And we want to glue these sections, and we could use a similar pushout diagram, but now we're going to use this diagram where this is a closed immersion, and this is just a finite map. So we're really using Ferran's setup of where one map is a closed immersion, the other is finite, to get the existence of the pushout. And then the local calculation is similar, but a little bit different, right? And I've sort of gone through the calculation here, right? I need to compute the fiber product of A and A adjoin T over A cross A, right? B here is A cross A, whoops, is A cross over A cross A with A adjoin T. And you realize it sits as a subalgebra of A adjoin T because, A itself is a subalgebra of A cross A. And then in this computation, you realize which elements of A of T live in the pushout. Well, it's functions whose valuation at 0 is the valuation at 1, because I've glued in the two sections, constant sections 0 and 1. And then one just works out this computation, sort of inspired by the calculation of the normalization of the nodal cubic, and one just can work out the local, one could show that there's generators X and Y that satisfy this equation, and so you see that it's a nodal family. And the Proj construction is similar here. And I don't want to give you the idea that these are easy arguments. There's a lot of details, and I am skipping details. And I think, as is clear, when you press me on some of these details, I don't always have the answer either. So these are genuinely challenging statements. But any questions? All right, I think we're in a good situation. I think we'll have enough time for a discussion today. But I'd like to summarize what we just showed. We showed that there's two morphisms. Again, I got this is G plus 1. There's two morphisms allowing us to glue sections together. And one reason why we care about this is that it'll allow us to define boundary divisors. So on the right-hand side, in particular, if I look over here at the definition of delta I have a map that glues in a genus I curve to G minus I curve at one point. So let me maybe say, as an example here, delta I. So yeah, I've defined delta I as the image of this gluing map. So it contains curves that look like this. So is it a genus I component meeting a G minus I component at a point, at a node. And so this is an example of something in delta I. Right, but using the other gluing map here, I define delta 0, and it contains curves that look like this. This is in delta 0. But note that okay, so I've only defined delta I and delta 0 as closed sum stacks of mg bar. It's a fact that it's a divisor, and in fact that there's so I've highlighted this in the bottom, that it's sort of an important fact. We won't prove it, and we also won't use it, that this boundary divisor is a simple normal crossings divisor. So this encodes two things: one, that it's a divisor, that's codimension 1, and two, that these divisors intersect transversely. So for instance, like to see that they actually intersect, you have curves, maybe if you take a genus I curve and then meeting another curve that has a node like this, this is an example of a curve that's actually in delta I intersect delta 0. And so we'll kind of use the fact that they do in fact intersect later, but it is sort of an important fact that they intersect transversely. This is a calculation that you can show using, well, I think maybe using Schlesinger's theorem and explicitly computing a universal deformation space and showing that yeah, the nodes are, each node defines a single equation. Right, so one reason I'm saying this is because we're going to use the boundary in a fundamental way in Wednesday's lecture when we discuss irreducibility. So,
question here.
Mhm.
Do you run into trouble that delta 0 has a self-intersection, so it's not like simple normal crossings?
Oh, you want me to erase simple? Wait, hold on.
I'm not sure what it means, simple normal crossings, I guess, in this context.
I mean, I just want to say, maybe I'm using the wrong vocabulary. Yeah, I just want to say that like formally locally around that point, that your equation, you have like power series ring and n variables, and your divisors cut out by the product, like x1, x2, all the way to like xk. Is that, maybe I should just drop, you're worrying me here, but. Yeah, let's discuss it at the end. Any other questions? Okay, the last map we want to discuss is the map where you forget a point. So here we'll talk about forgetting a point, and even we'll show that as a universal family. But I wanted to highlight first that this is sort of a subtle point, that forgetting a marked point can destabilize your curve, right? Example would be, just take a curve that has a rational component and a marked point here, right? If you forget that point, it's no longer stable. On the other hand, we do know what the universal family of MG bar is. We do have a stack theoretic description of it. So let's let UG be the universal family. So we know as a stack, UG parameterizes diagrams like this, where C to S is a stable 0-pointed family. So you're stable without the section. And sigma is just an arbitrary section. It could land in the singular locus. Right, and so we have sort of a natural map from MG N1 bar to the universal family, where you forget the point and you contract the rational bridge, or you contract all rational bridges. Right, so this ascends a curve like this, where you contract the rational bridge, and then you just follow the image of the point, and it goes to the node. Right, so we have a map from MG1 bar to UG, and it associates, right, to even a family. So this is now a stable 1-pointed family. And then you map it to to the stable model, obtained from contracting the rational bridges. And what we want to show is that this is in fact an isomorphism. So this is sort of, one should view the fact that MG1 bar is a universal family over MG bar as a much more remarkable fact that that MG1 is a universal family over MG. Because of this fact that forgetting a marked point can destabilize the curve.
Correct.
And so again, is there a question?
Yes. What is the definition of universal family?
Okay. The definition of a universal family is that any other family. Let me write it down here, just because I need this space here. MG bar universal family means that if given any other family of curves C over S, then there exists a unique map to MG bar such that this family is such that your family is the pullback of this given family. And it comes tautologically, this comes from Uneda's lemma. The 2 Uneda lemma.
So in particular, UG is an algebraic stack and UG to MG bar is a smooth, no, not smooth, a nodal family of curves, right?
Exactly, yeah. Right. So yeah, so I've spelled out what it is as the stack, but we know UG is an algebraic stack. And this is then a proper, flat family of curves, whose fibers are nodal.
And is it possible to verify this property directly? Because, for instance, so you gave us an exercise for MG, right? To prove that MG1 is the universal family. And in that case, we could do that by hand. Is it possible here? Why do we have to?
I think my point is that it's not possible here. Sort of the fact that one of my points was that MG1 is a universal family over MG, followed from tautological reasons. And if you apply that same logic here, you get a description of the universal family, but it's not MG1 bar. It's this. It's stable 0 pointed families and an arbitrary section.
Yes, thank you.
And so what's sort of remarkable here is that this map, this contraction map, is an isomorphism. So in other words, given, and if you look at this diagram, it's sort of easy to see that this is going to be a bijection on points. It's sort of but one thing that's hard is to explicitly construct an inverse. Like if I'm given a stable family such that the marked section is a node, conceptually it's kind of clear what you do. You just insert a P1 in there, right? And you mark one of the points in the P1. But defining that in families is really subtle.
So it's part of the issue that if you have a node and that node is one of your marked points, then it can't be a stable curve.
Right, yeah.
So then there's a unique stable, what you're saying is basically there's a unique stable curve where you are blowing up that point to get a P1 somehow.
Yeah, exactly. Yep, there's a unique, and some people call this, the stabilization of that, and even, so maybe it's clear what to do on points, but you can also imagine that, in families, you blow up that point to insert P1s, right? And that you can actually, I'm going to give 2 arguments here, but there is a third argument that essentially reduces it to a blow up calculation and doing sort of this local coordinate calculation to show that that blowing up works. But the 2 approaches I'm going to give are, I'm going to give a Proj construction following Knudsen, on the right hand side. So let me try to explain this. So here's the strategy: is to explicitly construct an inverse, And so we have a stable curve and an arbitrary section. And so what we need to produce then, yeah, is a stable one-pointed family. And so what we do is I'll let I sigma in OC be the ideal sheaf defining sigma. And then, okay, then you define K as follows. So you have a map from OC, because the ideal sheaf includes into OC maps to the dual of I sigma. And then I could also map via the identity to another copy of the structure sheaf, and I take K as the quotient. Okay, and then I define, or Knudsen defines C tilde as the proj of the algebra generated by K, symmetric algebra of K. And then, there's a surjection from, if I take the pullback, let's see, if I take the pullback of K, maps to the pullback of K mod OC, which is identified via this exact sequence, if you think about it with the dual of I sigma mod O. And what you need to show, and this is one of the really hard parts of the argument, is that this is a line bundle. And so that this gives a section. Gives a section S, by using sort of the universal property of maps to proj, you get a section S to C tilde. And then what you need to check is that this is C tilde to S and C is the desired one-pointed stable family. And yeah, there's a lot of details here, and I haven't followed them all myself. Yeah, you can check in Knudsen's paper, but I'd like to give sort of a more conceptual argument for this. But maybe let me pause for a second. I mean, to me, it just seems like this is a magical construction. Like, yeah, I don't know. I don't have an intuition for why this works.
Can I ask a question first?
Mm-hmm.
In very simple examples, is it possible to see why I sigma dual mod OC is a line bundle?
Yeah, I guess, I imagine it is, yeah. Well, I don't know. Like even, yeah, the first thing to do is to see what this construction does over, yeah, not even in the relative setting, over a field. And there you're probably right that you can kind of just see that that's the right thing. So yeah, maybe that, I mean, I'm sure that's where the intuition comes from, is just working out examples over a field, or maybe over a smooth curve, and then just, yeah. But what I'd like to present now is a different approach that to me seems more intuitive. But there's just other details to check. So we're going to use it. We're going to try to give a deformation theoretic argument. And yeah, so I'm sort of confident that this argument works. But on the other hand, I haven't checked all the details myself, and I'm not following a reference here. So take that for what it's worth. Okay, so we're in the setting like we were before. We have a morphism, mg1 bar to ug, which contracts rational bridges like shown in green. And so let's let C prime, P prime be your stable one-pointed family, and then CP is your stable model, yeah, where you contract the rational bridge. And so the strategy here is to show that it's an isomorphism by showing sort of that it's proper and that it separates points and separates tangent vectors. And I guess you also need to show that it's proper and representable. Because we know that, because if for proper, the familiar fact that is that proper morphisms of schemes that separate points and tangent vectors are closed immersions will work here as well.
Sorry,
and
what
so
does separate? Sorry, what does separate points mean in here?
It means it's injective on points. If you give me 2 k points of the stack, then the image is 2 different k points of the stack. The 2 images are different.
Okay, thank you.
Right, and actually, yeah, of these things, we already know, like bistable reduction, we know both sides, like MG1 bar and UG, but they're both proper. So we get that this map is proper for free. One can check that the induced map on automorphisms is injective, so you can get representability. And also you can check that it's injective on points, sort of just directly, you just see, yeah. So the challenge is in showing that it separates tangent vectors. And that's where the deformation theory shows up. So let's assume for simplicity that there's only one rational bridge contracted, like in this picture shown.
Can I ask a clarification question?
Mm-hmm.
So like if the bridge weren't a rational curve, but if we're positive genus, this would be very false, right? This sort of contraction. Because
yeah, right. Then this map wouldn't even, like if you had a different curve like this, where this is maybe genus 2 and a marked point, right? Then the image, you wouldn't contract this. You would forget that point, but you wouldn't contract.
Right, okay, good. Yeah, because in that case, right, that marking different points gives you non-isomorphic curves, whereas in the rational bridge case, marking different points on the bridge gives you the same curve up to isomorphism, right?
Exactly. Yeah, I think what Ben's pointing out is that like the reason this separates points is it doesn't matter which point in this P1 you mark, because any 3-pointed P1s are isomorphic.
Okay, great.
All right, so here comes the fun part. We need to show that this induced map on tangent space is injective, or well, it will be bijective. And we use an identification of the tangent spaces with the X groups. And here one needs to be careful because, especially on the UG side, where the marked point isn't even, it could be a singular point, but you still have this description of the tangent space as an X1. But note that here, while this is a line bundle, the other side is not. And so the properties we're going to use under this contraction map are listed here. So the C prime to C is contracting that P1, and we have the push forward of the structure sheaf is the structure sheaf, and you have vanishing a higher direct image. And also the push forward of the ideal sheaf defining P prime is the ideal sheaf defining P, and also you get some vanishing. And we want to compare their sheafs of differentials, and since we're contracting just one rational bridge, we have sort of an exact sequence like this that you can check. And so let's compute what the map on X is. So let's take an extension of OC prime by IP prime. So let's take.
Sorry, can you explain why IP prime is not a line bundle?
Well, because I think the point is it's a node, right? So locally.
I thought that was IP.
No. Right. Let me in this picture here. P prime is the smooth point, and P is the node.
Yeah. So
right, like yeah. Locally, it's not defined by just a single equation, right? You need both the x and y of the node.
Right. So IP is not a line bundle, but IP prime is a line bundle, or I think I'm not sure. I'm just a little confused because I think you may have written it the opposite way you just said it.
Maybe not. Well, yeah.
Oh, I see. Okay,
IP,
I get it.
Yeah, IP is not necessarily.
Sorry,
yeah,
it was my confusion.
Oh, no problem. Yeah. Okay, so let's suppose we have. Go ahead.
Sorry.
Go ahead and ask. I'll just write.
So what's wrong with the zeros of x plus y? So why isn't the node just the zero of x plus y?
No,
So we said that IP is not a line bundle because it's not the zero of one equation.
mhm.
This should be, yeah, I mean, yes,
That's
and
plus y
isn't the
cuts out the node set theoretically, but not scheme theoretically.
Does that handle it? Since I don't have much time, Alessio, can we just postpone this question to the discussion? Because I just want to make sure I can wrap up quickly. I only need like 5 more minutes. Oh no, even less. Okay, so let me try to wrap up this discussion. Again, we're trying to show that this map separates tangent vectors, and so we need to analyze this map on tangent spaces. We're going to show that it's a bijection, and we need to then show that this map on X is injective. Yeah, the goal is to show that this map on X is injective. And so we start with an element on the left-hand side. So this is just some arbitrary extension. Oh, let me make sure my indexing is right. Omega C prime. Okay. All right, and so what is this map on X? What does it do? So I can push forward this exact sequence under pi. Pi is my map from C prime to C. Yeah, let's call, yeah. Pi is the map from C prime to C. So I push everything forward under pi. And because of these properties, it remains exact. And, but on the other hand, I know I have a map from omega C here, and I define E as the Cartesian product here of sheaves. This is all living on C. And this I know is IP. And so this is the image, right? This is, yeah, the image extension, or this that lives in X1 of omega C IP. Ooh, all right, so that's what the map on X does. So let's suppose that it maps to the 0 extension. Let's suppose E is the trivial extension. That implies that there exists a section S here. So then we analyze this map. We know that the kernel of this map is just one copy of the residue field. So if we can show that residue field maps to 0 under this section, then this descends to a section S tilde. So you check that S descends to S tilde. And now we want to relate sort of, this section to possibly a section of this, because the goal is to show E prime is also the trivial extension. And so I think here you can use a junction that we want to construct. So we have S tilde, which is a map from pi push forward of OC prime to pi push forward of E prime. A junction tells you that this is the same as homomorphisms from the pullback of the push forward of OC prime to E prime. And then, so that gives you a map from pi push pullback of the push forward of omega C prime. So we get this map. Let's call this S tilde by junction. And then the last step is you check again by understanding this adjunction map that the map descends. Okay. I'll say S prime. And therefore E prime is also trivial. Again, there's a lot of details to check, but just sort of a different set of details in the first approach. But this is what I want to cover today. So I'm going to stop the recording.